So yesterday we looked at Boyle's law. If you kept temperature constant, what happened to pressure and volume? Today we will look at Charles' law. If you keep pressure constant, what happens to temperature and volume? This law explains how hot air balloons work. Who's ever seen a hot air balloon being inflated? What's so strange about it? It's on its side. Yeah, so you have the basket and you have some ropes like this, and you have a heating unit that rotates. Then you have a very deflated balloon on the field. I actually saw it in a indoor arena. That was kind of neat. And so they start heating it up. Okay. As they heat it up, what do they do to the air? This is free. Air can come in. It's no problem. What do they do to the air? It heats it up. Okay, so what happens to molecules when they heat up? They move faster. Okay, so what happens to molecules when they move faster? Yes?
They expand out.
They actually, molecules don't expand.
Well, I mean,
okay, what do molecules? They move faster, and that's the key. As they move faster, what happens when they hit the side of the container? Okay, the container is going to expand, not the molecules. You got to be careful. I know what you were talking about, Max, but you have to be careful how you say it. The container heats up. I'm sorry, the container begins to expand because the molecules are able to push it apart. This also explains if you've ever taken a shower in a walk-in shower. You walk in. Mine is like a coffin. Every day I take a shower in this coffin. Okay? The shower curtain. And then I start taking a shower, and pretty soon the bottom of the curtain starts kind of doing this, going in toward it. It is. Okay? There's air getting in, and I can feel my feet getting cold. Why? Very good. I am heating up the air inside my coffin with the water, with the hot water. As that hot air heats up, as that air heats up, what happens to its density? Let's see. Density is mass over volume. Does the heat from the water change the air mass in any way? No. What does it do to the volume? So the numerator stays the same, the denominator gets bigger, so what happens to the density of the air? It goes down. All right, so it inflates, and pretty soon it looks like this, right? What makes it go up?
Because it's less dense than the air.
Okay, it is less dense than the air around it. So what?
So that means that it would have to,
So this more dense air settles in underneath it and begins to push it up. Yeah. Okay. So how does the hot air balloonist come back down?
Don't they stop
You stop heating it, then the air cools down. When it cools down to be close to the temperature of the air around it, it starts to come down by its own weight. Right? So what happens if the hot air balloonist gets this family up there, several hundred feet up in the air, and the girl's pregnant, and she's about to give birth, and all of a sudden her water breaks, and she starts screaming. She's about to give birth. Get this balloon down here, down there now! How can the hot air balloonist bring it down fast?
Slow her down?
I don't think so. Do they?
yeah, there's a little cap on top.
So they can actually, so they can come down really fast? I thought they were pretty much dependent on just it cooling down naturally. Yeah. Either way, I don't think that he can bring her down very quickly. She may want him to come down quickly. They ain't coming down quickly.
Why is a 9-month pregnant woman on a
Well, if I was a hot balloonist, I would not allow 9-month pregnant women in my balloon. Okay. Charles Law was named after a French scientist by the name of Jacques Charles, and he was famous for the first solo flight and the first hydrogen-filled balloon.
This is a quick illustration of Charles' law. Charles' law is the relationship between volume and temperature of a gas. We're going to keep the pressure constant, and we're going to keep the number of moles constant. As you see here, we have our classic illustration of piston and cylinder, where we entrap a certain volume of gas at a given pressure. In this particular diagram, we're going to now add heat to it with some fire or whatever you want to do to heat the temperature up. And then, as you can see, as the molecules become hotter, they have more force, they travel quicker, they lift the piston up to a much bigger volume. And so this illustrates the fact that when you increase temperature, you increase the volume. And then if you allow it to cool, take away the heat and allow the gas to cool, the gas will now fall back to a smaller volume as you go to a smaller temperature. So temperature and volume are directly proportional. You increase one, you increase the other. And if you want them to be directly proportional exactly, you got to use absolute temperature. So you use the Kelvin temperature. If you double the Kelvin temperature, you will double the volume. And this little illustration here shows you the volumes going up by twice and going down by half as the temperature does the same.
Basically, we've already talked about Charles's law. As you increase the temperature of gas, what happens to its volume? Okay, it increases. Yesterday, we looked at an inverse relationship. Is this inverse or direct? This is direct. As one goes up, the other one goes up as well. As one goes down, the other one must come down as well. So here's that hot air balloonist, increasing the volume, therefore decreasing the density of the balloon. Here's some volcanologists studying hot air as well. What's another field of science that studies hot air? Political scientists study hot air. Finally, I have told that joke. This is the third time. This is the first time people have gotten it. Very good. Thank you, Marie. Thank you, Natalie. You guys are bright enough. Political scientists study politics. Politicians. Hot air. Get it? All right. If Boyle's law looked like this, what will Charles' law look like?
straight line?
A direct. Here's something interesting. When they started experimenting and we discovered how to supercool things, we discovered that helium condensed around -273. Methane condensed around -90, but if you extrapolate that diagonal line, isn't that interesting? Water condensed at 100, but if you continued on, hydrogen condensed around -273, and dinitrogen monoxide condensed around -110, but if you extrapolate the line,
So 0 degrees Kelvin.
so it would seem that it did not matter what gas you were dealing with. They all extrapolated back to one point. So if you ever wondered, how do we know that -273 is absolute zero? That's how. All lines lead back to -273. It doesn't matter what the gas is. It might condense before -273, that's fine, but if you keep the line moving all the way back, they all go back to negative 273. So, keeping in mind that there's a bunch of stuff that can have negative temperatures in Celsius, what unit should we use when dealing with the gas laws? Why? Kelvin, the coldest temperature you can achieve is negative 273. If you're going to play around with negative numbers, it is possible for you to have negative pressures and negative volumes. And you can't have negative volumes. So the safest, easiest way to deal with this, and I'm making it sound like it's voluntary. It's not voluntary. All the gas laws are based on temperature being Kelvin. If you use Celsius, it doesn't matter whether you did the algebra correctly. You will be wrong. You will be wrong. All gas laws must use Kelvin. So when we use Kelvin, everything extrapolates back to 0. We have positive numbers. All right, here we go. Let's remember what we did yesterday. Pressure was equal to K over V, where K made sure that whatever you did to pressure, you did the opposite to volume, right? That's the whole role of K, to make sure that whatever you do to pressure, you do the opposite. That's an inverse relationship. So we then said, okay, P over V, PV equals K. So, no, sorry. PV equals K. Get V over to the other side, PV equals K. That's Boyle's law, right? An inverse relationship. So, how do we show a direct relationship? Do we put temperature down here or do we put it up here? So what does K do for us here? It makes sure that whatever we do to volume, we do the same thing to temperature. Does that make sense? So, getting T over to the other side, Charles' law is V over T equals K. V over T equals K. The most useful way to use Charles' law is to say, hey, since the initial conditions equal K, hey, since the final conditions equal K, hey, the initial equals the final. Charles' law. If pressure is constant, something has to stay the same. 3 levels of difficulty here. 3 levels of difficulty. Level number 1. This is as easy as they get. A 2-liter volume is collected at 298 K temperature. It's cooled down to 278 K temperature. The pressure remains constant, so that means we can cross it out. Does the volume increase or decrease? Okay. What happened to the temperature? Down by a little bit. Therefore, the volume must go down by a little bit. All right. So, V over T equals V over T. 2.0 liters over 298 Kelvin equals X over 278 Kelvin. Cross multiply, X is equal to
1.8.
all right, how do we deal with sig digs here? How many sig digs did they give you the volume in? How many sig digs did they give you the temperature in? What do they want? Give them in 2. So if they give it to you in 2, give it back to them in 2. If they give it to you in 3, give it back to them in 3. So You said 1 point what?
9.
Does that make sense? Temperature went down by a little bit. Therefore, volume. Did it go down by a little bit? Let there be power. Level number 2. Let's read it together. Let's see if we can figure out why it's a little bit harder. A sample of gas at 15 degrees C, T, at 1 atmosphere, pressure, has a volume of 2.58 liters. What's that? V. The temperature is then raised to 28 degrees C, T again, at 1 atmosphere. What happened to the pressure? Cross it out. Does the volume of gas increase or decrease? Well, what happened to the temperature? The temperature doubled, so the volume must double. Or did it?
Because it's in Celsius and not Kelvin.
Awesome, Phoebe! That would be wrong for us to estimate it that way. What makes this level 2? Before you can even think about it, you have to convert to Kelvin. This is 288, and I think this is 301. So now ask yourself the temperature, the question. Did the temperature increase? By how much? A little bit, okay. Therefore, the volume should increase by a little bit. All right, so 2.58 liters over 288 Kelvin equals X over 301 Kelvin. Am I right? How many sig digs did they give you the volume in? 3. So you should give them back in 3. So what is it? Did that go up by a little bit? That's level number 2. Level number 2, they just give it to you in Celsius and they ask you to, you're going to have to, they don't even ask you. You're going to have to convert to Kelvin. This is not an optional thing. Level number 3, in former times, gas volume was used as a way to measure temperature using devices called gas thermometers. Consider a gas that has a volume at 35 degrees and a 1 atmosphere of pressure. What is the temperature in degrees Celsius of a room where this volume, the gas have a volume of 0.535 liters? Oh, so since they want it in Celsius, we don't have to change it to Kelvin, right?
No.
No. Okay, what makes it level 3? We're going to have to change it to Kelvin. 303, 308?
Yes.
Okay, so change it to Kelvin, do the math, and then change it back to Celsius. Yes.
Okay, so, so why does it, do you have to do something different if the, like if there's different amounts of pressure?
Yes. If the pressure changes, then we're in trouble. We have to use a different gas law. Actually, we're going to study next week that there is another gas law that has pressure, temperature, and volume. A gas law that combines them all. It's called the combined law, named after a famous scientist called James Combined. No, I'm kidding. There was no such thing. It's combined law because it combines everything. Okay, for the moment, we're keeping it simple. X equals,
A number.
well, the volume went down by a bit, so the temperature must go down by a bit. What is that bit? Okay, people should have their calculators out and they should be working on this. Okay, let's go to Kelvin first. What does x equal? Okay, 0.1 Kelvin. So when you subtract 273 from it, what is it? 28 point. Okay, but they gave it to you in 2 sig digs. 29. Behold, the 3 levels of Charles' Law. The 3 levels of Charles' Law. The 3 levels of Charles' Law. Avogadros Law. Behold, a balloon. This is Avogadros Law. Temperature, stay the same, please, for the next 30 seconds. Atmospheric pressure, please stay the same for the next 30 seconds. Volume. So as I put more molecules of gas in here, what happens to the volume? So if I double the amount of gases in here, the volume, if I have it, so temperature and the number of molecules are also directly related, right? Avogadro, when he was studying gases, he came to a marvelous conclusion. Very important. He basically said this: it doesn't matter what gas you are, you're going to act the same. Think about it. Gases are individual particles in the air. They barely ever interact with each other. When they do, they just collide and keep on going. Does it really matter whether it's Ryan gas molecules or Molly or Morgan? No. It doesn't matter who you are. All that matters is how many of you they are. Now, his students went on to take a lot of the ideas that he came up with and make them practical. One of his students invented a barometer. Later on, I think several of his grand students came up with Avogadro's number. This law that we're going to talk about, he actually didn't do. Okay? His students created it based on his research. So what is the relationship between the number of molecules and volume? Direct. The greater the number of molecules, the greater the volume. What is a good analogy that we can use to remember this? Inflating a balloon. Inflating a balloon. All right. So, what should this look like? First of all, do we want to play around with the number of molecules? We're talking about a bunch of zeros. What's a unit that would be a whole lot better to use than molecules? Moles. Moles. So, here is Boyle's law. No. Here is Charles' law. So what's Avogadros' law going to equal? V is equal to K. N is the symbol we will use for number of moles. Is it going to be here or down here?
No.
If it's here, that means that K will make sure that whatever you do to volume, you do the opposite to the number of moles. Is that what you're trying to say? No. So you need to put it beside it. K will make sure that whatever you do to volume, you do the same thing to the number of moles. So, behold, Avogadro's law. where N is taken over to the other side. A direct proportionality. Yes, it's usually seen as a cursive N. I'm sorry. Okay.
Sounds like an H. That's an N. It's an N. It's
Oh,
always
that's
an
an
N.
O.
We told you it's an N. Wait, it's supposed to be an N? Yeah, it's supposed to be an M.
Number of moles.
Oh! Oh my god.
Okay, so as the number, you see what I was trying to say? It's in italics. N. As the number of moles increases, what happens to the volume? And if you triple the number of molecules, okay, here we're going to go straight from level 1, level 0 to level 4. Levels 1, 2, and 3 are going to be very similar to the ones we've already seen. Let's figure this one out. Just one. You've already seen easy examples. Yes. So this is level 4.
You just said there's only one level then.
That I'm going to show you. I'm not going to show you levels 1, 2, and 3 because they're very similar to Charles. Okay? But Charles can't go here. You'll see why. We have 12.2 liters, that's volume, containing, that's N, at a pressure, P, and a temperature, T. All of this oxygen is converted to ozone. Right there, that tells you that's a little weird. We've not seen one like that. At the same temperature and pressure, what does that allow us to do? That allows us to cross it out. We don't need it. If a variable does not change, then we don't need it. What will be the volume of the ozone? Okay, so this is Avogadros Law, moles and volume. Let's do this. 12.2 liters over 0.50 mole. It's V1 over N1 equals V2 over N2. All right, they want to know what the new volume is if the number of moles is okay. They didn't tell us how many moles we have at the end. Okay, now wait a second. All right, hold on. Marie says, wait a second. We know that O2 converts over to O3. We've done questions like this before where I give you the moles of one thing and I ask for the moles of something else. Right? So we can start with a train track. We have 0.50 moles of oxygen. We need to convert moles of oxygen to moles of ozone. Now wait a second. This is like going on that trip through Europe, right? But here we already have it in the international unit of mole. So this is that middle section of our long train tracks. But where do we get these numbers? That's the exchange rate. Where do we get that exchange rate? From the balanced equation. Very good, Noah. Did they give us a balanced equation? No. Can we figure one out? 2 O's, 3 O's. So 0.50 times 2. Do we convert it to grams? No. Don't convert it to grams. They don't want grams. We need moles. Leave it in moles. We're done. We're almost done here. I think this is 0.33 moles. But wait a second, Mr. Moreno. I mean, this is moles of oxygen. This is moles of ozone. Can you do that? Yes, because did Avogadro care what kind of gases they were? No, they were going to act the same. They were going to act as if they were the same. Avogadro tells us, it doesn't matter. It doesn't matter. All you care about is the number of moles. All right, so since the number of moles go down by a little bit, what should we expect the volume to do? Okay? And that is? All right.